Okay. Orientation is up. Vertex, -2, -3. Focus, -2, -2. Okay?
Date. Date. Need the date.
Error bars just like.
23?
Yeah.
I'm not sure what it is because my watch periodically resets itself to January 1st. And when I go to find any instructions for how to reset this thing back, there is no name on this watch anywhere. So this is a rather cheap watch, so I get what I pay for. All right. All right, 4 and 5. This is a hyperbola. This one, I think I did one of these. I hope I did do one of these. And I said the thing you got to be careful about is when you complete the square on the y's, if the y is the thing that's preceded by a minus, the kind of thing you got to do is this. Because in order to complete the square, you need the coefficient of the y squared term to be a +1. All right? So you have to take out the -1, so to speak, put this in grouping symbols, complete the square by adding 4 inside. But when you add 4 inside, what have you really done to the left side? You've subtracted 4. So you got to subtract 4 from this side. I'm not going to do it, Liam, because everybody made that mistake, and I'm not going to get partial credit for that mistake. Because I'm not. Minus. I don't think that was very comprehensible, but it's the one thing, it's the error to avoid. You know what I mean?
Yeah.
You know? So that's equal to 1. You get a y minus 2 squared inside here. And if you multiply this out, you'll end up with what you started with. Okay? You'll end up with a minus 4y inside, but you got to subtract it, so it's a plus. If you have a plus here, it doesn't work because you end up with a minus up here, okay, and it just doesn't work. The center of this hyperbola is 0, 2. The orientation is left-right because the x squared is what's first. So the orientation, so it looks like this. Say that again. Go ahead. Questions?
No.
Oh, okay. It's the center is 0, 2. It goes like this. Okay, with left, right. All right. So the answer to 4 is A, left, right. The center is 0, 2, B. Okay. Anybody else sit on that? I'm sorry. Yes.
I don't know if you can, if I can get the partial credit for 5 for this, because I have it on here is the.
You have, if you had 0, 2 written down or something to that effect, I would certainly consider that. But it seemed to me almost everybody just made the mistake of
It's in what I have written down.
the same mistake.
Add 4. Subtract.
Oh, okay, so.
But I just don't know.
Yeah, wow, that's not too bad. Oh,
If it's
well, the y plus 4, you have the y plus, you have a y plus 4 here, you got a y plus 2 here. Why do you get y plus 4 over here? And then you got a 9 here, which says to me you added 4. What you want to do? That's not good enough.
I think I maybe.
Let's see. The parentheses, that's good. You added 4, you subtracted, that's good.
Okay. I don't know why I put that here.
This man deserves partial credit.
Thanks, Brandon.
Last name?
Santiago.
What is it?
Santiago.
Okay. Yeah, he had, Brian, he had it. Okay. Let's go on. Circle. 6 and 7. We have a circle, x squared minus 8x. y squared equals 9. Complete the square. Take half the coefficient, negative 4, squared 16. Add 16, x minus 4. Okay. You have a center of 4, 0. You have a radius of 5 on this circle. Center 4, 0, radius of 5. Okay? That should be pretty straightforward. 8 and 9. Given x equals 2 cosine, y equals sine. All right, we want orientation, and we want to solve it in rectangular form. Actually, what I'm going to do is put it in rectangular form first, so I know what the thing looks like. I'm going to divide both sides by 2 here. I'm going to square both sides. I'm going to add these up so that I have x squared over 4 plus the y squared equals sine squared plus cosine squared, which is 1. And what we've got here is an ellipse. Okay, so we know what it looks like. We've got an ellipse, semi-major axis of 2, minor axis of 1. So we have this. The question is, what's the orientation of this ellipse? And the way to do orientation is start theta somewhere. Let's start at 0 typically. Start at 0. When theta is 0, x is 2 times the cosine of 0. Cosine of 0 is 1. So x is 2. The y would be 0. So we're starting here. Increase theta. When you increase theta, cosine decreases. So the x will decrease. Move to the left. What happens to the sine as you increase theta? The sine will increase. So the y will increase. So it's going to go from here up this direction. Okay? And what that is counterclockwise. Okay? So the answer to 8 is counterclockwise. The equation in rectangular form, x squared over 4, y squared, you can put it over 1, usual form for an ellipse, equals 1. Okay? Okay. Everybody else set with this? You okay, Omar? 10 through 12, you're given the parametric form. Where x is t squared, y is 2t cubed, and we want to find dy dx. And again, there are a couple ways to do this. One way is to eliminate the parameter, get y in terms of x directly. You take the square root, but you get plus or minus. It's a little iffy, I'd say. You could do it that way. I think the better way is to use the chain rule here. So you get dy dt, dx dt. dy dt, 6t squared. dx dt, 2t. We'll end up with 3t. Okay? And we want to know at t equals 2. That would be 6. So, slope of the tangent line, dy dx, at that point where t equals 2 is 6. We want the second derivative there. Determine concavity. So, second derivative. What do? You take the derivative of the first derivative with respect to with respect to t, rather, I'm sorry, and take the first derivative with respect to t. The difference here is we're taking the derivative of the first derivative now with respect to t, as opposed to taking the derivative of y with respect to t here. Here we want the first derivative, which is the derivative of y, okay, with respect to x. Here we want the derivative of the first derivative with respect to x. So that's what we put in here. Instead of a y, the first derivative. So take the derivative of dy, take the derivative of dy dx. Geez, I'm going to get this right, one of these things here. Okay? dy dx, the derivative of the first derivative with respect to t. Here's the derivative, here's our first derivative. Take its derivative with respect to t, 3. Take the dx dt again, 2t, and take t equals 2 again. to get 3/4. Okay? D is the answer. I'm sorry here. Okay? That's a dy dx. Okay? The derivative of the first derivative with respect to t over dx dt. This is the derivative of y with respect to t over dx dt. Yes?
When you're taking the second derivative of these, I'm sure you explained it, but it's just, I forgot. Why is it that the derivative of the x is only taken for the first derivative, and then you use the first derivative of the x and the second derivative of the y?
Yeah, that's a good question, but you have to think about what you're asking here. When you do the first derivative, you're taking the derivative of y with respect to x. And that's what I'm doing here, taking the derivative of y with respect to t over the derivative of x with respect to t. That's what the chain rule says. When you take the second derivative, now you're taking the derivative of the first derivative, okay? And that's what you have to put here. Instead of the y, it's the first derivative now. Everything else is the same. That's the only thing that changes. And that's what it is. Now, what you could do is eliminate the parameter and do this directly, and you'd get the same thing. All right. Okay? That's what it is. It's a little tricky, but that's it. Yeah. All right. Okay. Oh, and number 12. There's a 12 here. Arc length of the curve. Arc length is equal to. We are going from 0 to 1. We have the derivative dx dt squared. That's 2t squared. dy dt, 6t squared, squared, dt. Okay? Dx dt squared, dy dt squared. Okay? And just leave it like that. That's the answer. So that answer would be B. Okay? If you've got surface areas a little bit more complicated, 2 pi r, you got to multiply this by. But that's it for arc length. Okay? Everybody okay with that? 13 through 16. Given that polar equation, I think that's the one we did that in class, it seems to me. And what we have here is a cardioid. When theta is 0, r is equal to 2. Comes around, hits exactly at the pole, and completes this way. Okay? This point right here is pi 0. Cosine of pi is -1, plus 1 is 0. Okay? Okay, so what do we want to know here? Symmetry, polar axis. Cosine typically polar axis, cosine being the even function that it is. What graph is it? It's a cardioid. Okay? The value of x in parametric form, you put these in parametric form by x equals r cosine. R is 1 plus cosine. So in parametric form, x is equal to 1 plus cosine times cosine. That would be C. Integral for the entire area. And I added the word entire because when I changed the test around somewhat, I added entire because it was a problem before, I remember in previous classes. So I put the word entire for you guys because I like you guys, all right? So I put the entire. That meant you got to do the whole thing. So what's the area? The area is 1/2. That's the formula. But we're going to go from 0 to pi. We have to double it to get the entire area. Okay? We're going to go 0 to pi, and we have to take the function squared. 0 to pi is half of it. To get the other half, double it. To get both halves, to get the entire. These cancel. So the answer is C, I guess. Yeah, C again. Be okay with that? Yeah, Liam.
About that. So the reason I messed that up is because I was looking at a problem with 4-petal rows right before. And so since theta in the 4-petal rows is being multiplied by 2 in the argument, does that mean it's going to complete all 4 petals faster because the argument's being multiplied in the...
Yes, it does. It does. That means it's going to complete it in pi radians
Right.
to get to 2 pi. Yes, it does. Oh, and then if you double, yeah, I see your point. But there's two different situations. Yeah. All right, good question. All right, 17 through 20. Okay, here we go, 17 through 20. R theta equals sine theta. We're talking about a circle. Wow, it's a pretty good circle. Okay. Or a rose of a single petal, if you want, if you will, because it could be considered that way. Symmetry, theta equals pi over 2. It's the y-axis, okay? Typical with sine functions, polar equations with sines. Sine is an odd, okay? An odd function. You get symmetry with respect to theta equals pi over 2, okay? What graph is it? It's a circle. Slope of the tangent line, oh boy. At pi over 8, we want the slope of this tangent line at that point right there. Well, you find slopes of tangent lines by finding dy dx. We have r equals sine, and we need dy dx. And the way to get dy dx is to change this from polar form to parametric form. So here's what we have to do. X is equal to r cosine, r is sine, so you get sine cosine. Y is equal to r sine. So y is equal to sine times sine, sine squared. The derivative, the slope of the tangent line, is dy d theta over dx d theta. Chain rule. Dy d theta, you're taking the derivative of sine squared. That's 2 sine times the derivative of sine, which is cosine. Okay? You okay with that? Over dx d theta, the derivative of sine. What's wrong, Dylan?
I'm just saying, can't you just take dr d theta and it comes out approximately the same?
Approximately the same.
So I got like 0.9 something for dr d theta pi over 8, and then I got 0 for dr d theta when it's at the pole.
That would be reasonable. The first one is a coincidence.
Okay.
Okay? It's a coincidence. If you take dr d theta at pi over 4, the actual slope of the tangent line is undefined, but your dr d theta is going to be cosine of pi over 4 squared root of 2 over 2. It just doesn't work. Okay? Dx d theta is equal to, we have a product rule here. First derivative of the second plus second derivative of the first, which is a cosine. So you end up with 2 sine cosine, which is sine 2 theta. Cosine squared minus sine squared, which is cosine 2 theta. And that's equal to tangent 2 theta. Now we did one like this or like this, where we said it's always going to be a tangent of the argument. Did we say it like that? It was something like that, we said it. So what do we have? Pi over 8. Substitute in pi over 8, we get the tangent of 2 times pi over 8, tangent of pi over 4, which is exactly 1. Okay? Exactly. So that's what it is. Okay? Oh, and one more. Slope of the tangent line at the pole. Set this equal to 0. When's this equal to 0? At theta equals 0, which is this polar axis. And the slope of the tangent line at the pole, okay, is 0. Okay? It's this right here. The equation of the tangent line is 0 as well. All right, any questions? Everybody else set on that? Now, here's what you want to do. You want to keep this test. When the final comes around, and believe it or not, before you know it, it'll be time for finals, okay? You want to make sure you know how to do this stuff, okay? Because on your final exam will be questions from these hour exams, okay? Topics from these hour exams. There's nothing on a final that's not on a test, one of these tests. Don't.
What about polar coordinates? Are we going to be using them throughout the course?
Say that again?
Are we going to be using polar coordinates throughout the course?
We come across polar coordinates in 3 space, in which case they're called cylindrical coordinate system. Yes, we will. We'll need them then. Absolutely, we'll need them. All right, let's go on. Next chapter. Next chapter is, it's interesting because it's a topic, vectors, that some people are very familiar with, and some people swear they've never seen these things in their lives, okay? So what we have to do, obviously, is to start at day 1, okay? And if I'm saying things that you're very familiar with, and you're sitting there bored, wishing you were anywhere else but here, just do what Anthony does in my class all the time. Just be thankful and be patient. That's all. What else can you do, right? Yeah. All right, let's take a look at these vectors. We'll do 2 space first. A vector is a directed distance from one point to another. This is called the initial point. It's called as P. To a terminal point, okay, Q. The direction makes a difference. Let's say P has the coordinates 2, 3. Q has the coordinates, let's say 5, 6. We can write this vector in what's called component notation, use components, and write it this way, PQ, this says start at P, end at Q, that's equal to, and what we'll do is take the end point, terminal point, 5 minus 2, end y minus start y, 6 minus 3, to get 3, 3. This vector, PQ, is equivalent to any vector in the plane with the same length and direction. When you put it as 3, 3 in this component form, this is called standard position. The standard position starts at the origin and goes to this point, 3, 3. This vector, I'll call this V. In standard position is equivalent to vector PQ. It's equivalent to every vector in the plane with this length and direction. So we can pick this up and place it anywhere in the plane for an equivalent vector. It wouldn't matter. What is the length of that vector? Its magnitude or length is equal to the square root of 3 squared plus 3 squared, which would be the square root of 18, which would be 3 times the square root of 2. That would be the magnitude or length of this vector. In general, if you have some vector W, the magnitude of W, bless you, square root of A squared plus B squared. Okay? Just really a distance formula is all it is. Well, what are we going to do with these vectors? We're going to add them, we're going to subtract them, we're going to multiply by a positive number, by a scalar number, some real number. What we're going to do is multiply 2 vectors. There's 2 ways to multiply vectors in 2 space. One is called a dot product. And when we get to 3 space, so probably tomorrow, we have also what's called a cross product of 2 vectors, okay? So let's do some of those things now, okay? You ready? First of all, everybody up? Okay. Let's start with some vector. Let's take negative 2, 3. Let's multiply it by some scalars, some real numbers. This is negative 2, 3. This point would be negative 2, 3. The vector itself is referred to this way, negative 2, 3. If you multiply by negative 1 and take the opposite of this vector, we're going to take the opposite of each component. We're going to multiply by negative 1. And when you multiply by a constant, you multiply the constant through the vector to get 2, negative 3. That vector would be 2, negative 3. It would take it out the other side. If this is vector v, this is the opposite of v. Okay? Takes the vector, turns it around through the origin to the other side. In general, when you take some vector and multiply by a constant, oh, rats, sorry. Let's take some vector and multiply by a constant. You multiply each component by that constant. Okay? If that constant is a number greater than 1, what happens to the vector? It increases. Same direction and increases in magnitude. It gets stretched out. If you multiply a vector by 1, what happens? Stays the same. If you multiply by a constant between 0 and 1, what happens? It decreases, shrinks, same direction. If you multiply a vector by 0, what happens? It gets a 0 vector, which is 0, 0, which is a single point, also called a degenerate vector. Okay? If you multiply by a negative number, it'll turn it around and take it out the opposite direction. Okay? Sometimes we're going to want a vector in the direction of a given vector having length 1. Okay? Sometimes a vector having length 1 is called a unit vector. A unit vector, an example of a unit vector, has a little hat. You put, generally speaking, for unit vectors, you put a little hat there for some reason. I don't know how that came about, but that's what it is. Unit vector, where the magnitude is equal to 1. Okay? That's a unit vector. So, if we have some vector and we want a vector in the same direction but having length 1, for example, let's say v is equal to 2, 3. Okay, 2, 3. This is vector v. But what we want is a unit vector in the same direction as v, but having length 1. Okay. What we do, you guys know what to do here? What do you do?
Divide by the scalar quantity?
Divide by the scalar quantity.
Magnitude?
Yes. Okay. You take the vector v and divide by its magnitude. Okay? And that'll give you a unit vector in that direction. Okay? Okay. You can do little proofs with these vectors too. It's kind of neat. This vector u, you're dividing by a magnitude. It's a positive number, so it's going to stay in the same direction. The question is, what's the magnitude of this vector? Here, let's take a look at that. How much? Ooh, I don't have that much time, do I? Yeah, I said it. I'm going to do it now. All right, so here we go. Here's what I want to do. Let's take this and find the magnitude of vector v divided by its magnitude. Okay? Where v, let's do it in general, is ab. So you got some vector v, and I just told you to find the vector in the direction of v having unit length. Okay? Take the vector, divide by its magnitude. That's what Liam just told you anyways. I want to prove that that is a unit vector by taking the magnitude of that. So let's do it. So we want to take the magnitude of v over the magnitude of v. And we want the magnitude of this vector. You ready? So I have this. I can divide each of these components by this.
Can't see it.
Whoa, 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 whoa. Okay, sorry. Okay, so I'm going to take this. I'm going to have a over the square root of a squared plus b squared, because that's what I can do when I multiply by a constant, multiply each component by that constant. I'll have the b as well. Now I've got this vector. How do I find its magnitude? I take the square root of the sum of the squares of the components. So I'm going to square this. These are fun to do. You know, you got some time sometime, you should just do a couple of these little proofs. Okay. Square each. And now what? Well, we got a common denominator. And we end up with 1. So what you've done is prove that the magnitude of a vector divided by its magnitude is 1. Okay? A unit vector. Just for laughs, you know what I mean? You can do that kind of stuff. Let's see, there's a lot more we have to do with vectors. Let's add two vectors. I'll do a couple. I just want to get through the first section here. Let's suppose we have vector u and vector v. Let's say here's u and here's v. Okay. Let's suppose vector u is equal to ab and vector v is equal to cd. You add the two vectors by adding their components. Okay. Okay. You add their components. Geometrically, what does this give you? Well, if you complete this parallelogram, okay, the sum of these two vectors gives you the main diagonal. This is u plus v. Okay. And if you take their difference, you realize that that's like adding the opposite. Okay. And let's check this out. If you take the opposite of v, we know what happens. You get this vector. Okay. Now I'm adding u plus the opposite of v. I'm going to complete the parallelogram. Take the sum, gives me this diagonal here. This is going to be u minus v. Back at the original, this vector and this vector are parallel with the same length, hence equivalent vectors. This is u minus v. It's the other diagonal to this parallelogram. Okay? Ooh, is that okay? Wow, I don't see one face in agreement, except maybe Dylan's. But other than that, here we go. U, V. The sum, complete the parallelogram, draw the main diagonal. That's the sum. The difference, complete the parallelogram. The difference is, start at V, go over to U. Okay? That's the only thing you got to remember. It's the other diagonal from V to U. Okay? It goes this way. And here's the proof of that. The proof of that is, well, instead of doing the difference, let's change it to a sum, which I did, which gives me this main diagonal, which is this diagonal up here. These two guys are parallel and same magnitude. Yes?
Can you do u minus v on a different sketch?
Say that again?
Can you do the u minus v on a different graph?
On a different graph? You don't like this graph?
Yeah.
Oh,
It's
all right.
hard to follow.
Oh, okay. Well, let's do let's do it in with real numbers here. Let's suppose u is equal to 2, 3, and v is equal to 1, 5. Okay. So here we go. 2, 3, 2, 3. Here's u. 1, 5. Here's V. Okay. The sum, when you take the sum of these two, am I still on the thing here? Add up the components, it'd be 3, 8. If you complete this parallelogram, okay, the sum, U plus V, is going to end up at 3, 8. This point right here is 3, 8. That vector, that is the sum, is the vector 3, 8. Okay? That's the sum. Let's take the difference. U minus V. Okay, if we take U minus V, that's going to be the vector 1, U minus V, negative 2. Okay? Now 1, negative 2, 1, negative 2 is this vector down here. But we can take it and bring it to here, as long as it's parallel with the same magnitude, here. Okay? If you start at V at 1, 5, and you go over 1 and down 2, over 1, down 2, you're going to be where? If you start here and go over 1, down 2 from here, you're going to be at 2, 3, this point right here. This is that vector right here. This vector right here is U minus V. Okay? Take this, put it up here, start here, it brings you to here. Okay? Is that good?
Good.
Brandon, thank you. Wow. Is that okay?
I hate to see you worried.
I know, I was concerned. I was. All right, I'll tell you what. That should get you started with the vectors. Some people have had them, like I said, for a long time. Some people haven't. That should get you started in 11.1. 11.
You want to write for that right there, vector U plus or minus vector V equals.
What's that? Say that again.
There's an equal sign, but you didn't finish
That,
that. That goes to U.
equals, where was it? Back here? I'll tell you what. Yeah, I don't know what happened here. U minus V would be A minus C and B minus D. That's what it is. I don't know what I did. Good question, Dylan. I don't know. Started it, and I don't know what I did. I must have zoned out or something. All right. Yeah, you can hear. Tell you what, Omar, you can have them all.
I just need that one page. I didn't finish the notes on it.
Where's my first page? Uh-oh.
I think
Oh, it was back. Oh, here it is. I got it. Don't panic.
doesn't say here.
Hold on a second. Jeez.
Pause the recording. Use up all your memory.
By the way, I didn't get